Okay, in this part I would like to discuss about the external flow. Oh, I guess I need to edit this one. So, previously we already discussed about the internal flow, and the main difference about the internal flow and external flow is the boundary conditions. So if we have like a walls around the flow, so it will be considered as the internal flow. But if we have like a free stream, so we have like inlet and outlets, and the object, which is the wall within or inside the boundary, it's called the external flow. But sometimes we can also modify the external flow by increasing or considering the ground. Let's say if we want to simulating a vehicle, road vehicle, or the Ahmed body, let's say. So we also have the wall, which sometimes like a moving wall with the velocity of the like the speed. But for like aerospace applications, the configuration is like this. So we can actually use the circular domain, but sometimes we can also use this like semicircle to accommodate the high angle of attack. So we can easily modify the angle of the flow or the angle of attack. And one interesting thing here that you must notice is that the inlet and the outlet has the same velocity and pressure, so it's called the free stream velocity. So you don't have to define the zero pressure outlet or zero different pressure between inlet and inlet, because in the free stream the velocity and the pressure will be the same for inlet and outlet, especially if your object is very small compared to the domain size. So one thing that you must consider is to make the object as small as possible and the domain as large as possible, so the effect of flow for the boundary is negligible. But the problem with that is you can use a lot of computational efforts if you use this kind of mesh. So sometimes we just make a highly extreme grading like this to accommodate the free stream velocity. So let's just check our case file. Actually, this file is not provided in the tutorial folder. I actually combined the airfoil 2D, but with the geometry and the block mesh from the NACA 0012, which is like this, NACA 0012. So I will provide the document or the folder in the description of this course, so you can use it. But if you want to copy that, you can also just copy the airfoil to the object, then copy and paste the geometry. Let me show you tutorials in compressive. I think it is in the fluid. So I just copy the airfoil steady here, the block mesh within the system folder. This one, I copy this, and also the geometry I get from the run. So within the run folder, you will have a script to copy and paste the geometry. But you don't have to do that because I already did that for you. So you just can download the file in this download the file inside this course. Okay, so here we go. Let's check our boundary conditions. So the velocity, the velocity is basically the free stream velocity, and one main difference maybe from the external flow, or in the external flow, is that the internal field, or the initial condition of the whole region, is not zero. So for the internal field, in the previous section we used the 0 everywhere for the initialization, but for this free stream condition we use specified velocity. And we also use the x and z direction based on the mesh orientation. You can check later. So for the angle of attack, you can calculate manually by using total velocity, cosinus and sinus of the angle of attack. Or the other way that you can do, if you are not using a block mesh, maybe using a different mesh, you can change the angle of the of the geometry itself. Or maybe if you want to use this, you can use a angle of attack calculator, but yeah, it is up to you. And the other thing that interesting here is we can use the value of the internal field as the input of the inlet and outlet value. So we use the $sign here, means that we are calling the parameter from the other inputs. Let's say this internal field, so we will input this uniform, etc. into this field. So it is the function of the $sign. And we can simply put the internal field here with the inlet and outlet, because the boundary condition with an inlet and outlet will be always the same with the internal field in the initial condition. Okay, so it will works perfectly if your object is far away from the outlet and inlet, because if your object is nearby the outlet, let's say like a wing with a weak region that is touch the outlet, the velocity itself will be not uniform. So you must take the object as far as possible from the outlet. And let's see the other parameters, which is the P, let's say. So the P, we input the free stream pressure. This is the same, they are the same, the inlet and the outlet. So the walls is just a zero gradient, because the pressure gradient will be calculated from the interaction of the flow and the wall. And let's check our velocity again, and we check the wall is no slip condition. So no slip condition is basically you can input also the constant velocity of 0, 0, and 0. Then we also have the no tilde here, and not, means that the parameter from the Spalart-Almaraz turbulent model we will discuss later. And that's all for the 0 folder. Let's check for the constant folder. We have here the geometry. I just like I said, I copied from the airfoil NACA folder. And also the other thing we don't have to worry about, the physical properties. Let's check. It's just the input of rho and nu, which is the kinematic viscosity. So if you notice from the previous course, we use a thermophysical, but here everything is temperature independent, so we only need to input the rho and the nu. And the momentum transport is Spalart-Almaraz, we'll discuss later. And we also, but a little hint about Palette Almaraz, is this like the simplest model that works well for the aerospace application. And for the system, I think we just copy the block mesh from the NACA 0012, and the other is the control dictionary. Let's check the start time, and we expect to stop at 500, and right interval is 50, so we will save about 10 files. And the FE scheme and the FE solution is basically just the solvers that we use. That we have a U, no tilde, etc, etc. Okay, nothing much to worry about. Just focus on the boundary conditions. Then we try to run the block mesh first. Let's open it. View. Oh, sorry, I mean touch. Home.com. Okay, let's just open our file. The foam.foam, which is the block mesh. From the original tutorial folder, we also need to do the extrude mesh to like increase the thickness, but I think we don't have to do that. And then let's just run our simulation. Okay, let's just pause while waiting until like 500. Actually, you can scroll this if you want to like pause the running and to check the simulation, or maybe you can also refresh here if like to check the updated number of iterations. And here we go, we finish our iteration and then just touch again. And this simulation is basically a steady state, so the number of time folders are not the actual time, but it is like just the number of iteration or number of cycle. Okay, just go to the last iteration. Let me slice it to the Y direction, and here we go. Let's see our result. I think it is extremely small, which is good at some point to to avoid the intervention. But sometimes if you do this small, the quality of the mesh will be like extremely thin like this. It is sometimes prone to error, but it's okay if you are not facing that error. Okay, let's just zoom in to our object, which is the NACA 0012 with the velocity like this. You can change the visualization like we already did in the paraview section. And the thing that you must check from the post-processing, that to make sure that this velocity or pressure distribution do not hit the edge or the boundary conditions, which is very extremely far away here, which is rarely can be done if you are using like complex geometry. So that's it.